Hi. Everything around you, your phone, your chair, the air you're breathing, the light hitting your eyes right now, is made of stuff obeying very specific rules. Rules so precise you can predict where a planet will be in 1,000 years. So strange they say a particle can be in two places at once, and so incomplete that the smartest humans who ever lived still haven't fully figured them out. That's physics. And you're about to get all of it in 20 minutes, without a single equation traumatizing you. Let's go. Start at the beginning. Not the Big Bang yet, that's the end of this video, but the beginning of physics as a discipline, which means the most important sentence in the history of science. Things move the way they do for reasons. That sounds obvious. For most of human history it wasn't. Things moved because gods pushed them, or because it was their nature, or because the universe just felt like it. Then came Isaac Newton in the 1600s, who sat down and basically said, no, movement follows rules. Here are the rules. They work everywhere, always. Newton's 3 laws of motion are the foundation of classical mechanics, the physics of everyday stuff at everyday speeds. Law 1. An object keeps doing whatever it's already doing unless something forces it to change. Moving stays moving, still stays still. This is inertia, and it's why you lurch forward when a car brakes, and why your coffee keeps traveling toward your laptop even after you let go of the cup. The universe does not change things for free. Something has to push. Law 2. That push is called force, and it produces acceleration proportional to how massive the object is. Push a shopping cart, it moves. Push a bus with the same force, it barely notices. The heavier the object, the more force you need to change what it's doing. This is why rockets need absurd amounts of fuel to move anything anywhere, and why a feather and a bowling ball fall at exactly the same rate on the moon, where there is no air resistance to slow the feather down. Mass resists change, always. Law 3. Every force has an equal and opposite force pushing back. You push the wall pushes back on you just as hard. You push the ground to walk, the ground pushes you forward. Rockets work by hurling gas out the back, and the equal and opposite reaction pushes the rocket forward. This is the entire operating principle behind every vehicle ever built. Action, reaction, equal, opposite. Newton also gave us gravity, not just the things fall version everyone knows, but the universal law that says every single object with mass pulls every other object with mass. The sun pulls on the earth pulls on the moon. You are pulling on Jupiter right now, extremely weakly, but you are. The force gets weaker with the square of the distance, which is why Jupiter doesn't notice you and why the moon is locked in orbit around Earth. Gravity is everywhere, always, between everything. It just usually gets drowned out by everything else in your immediate vicinity. Connected to force is energy, which is the capacity to make things happen. Kinetic energy is the energy of moving things. The faster and more massive, the more kinetic energy carried. Potential energy is stored energy waiting to be released, a ball held up high, a drawn bow, a coiled spring. Energy can change form, but it never disappears. That's conservation of energy. The total in a closed system stays constant. It converts, shuffles, transforms. It does not vanish. This single principle runs through every corner of physics and is possibly the most important bookkeeping rule in the universe. Closely related is momentum, mass multiplied by velocity. When objects collide, momentum transfers between them, but the total stays the same. A billiard ball hits another, slows down, and the second takes off with essentially the momentum the first one carried. This is why crashes are violent, why rockets in space can steer by firing tiny bursts in one direction, and why catching a fast-moving object hurts more than catching a slow one. Momentum is conserved, always. Let's talk about waves, because waves are how the universe communicates most things across distance. A wave is a disturbance traveling through a medium, carrying energy without permanently moving the matter itself. Drop a stone in water and the ripple travels outward, but the individual water molecules mostly just bob up and down in place. Sound is a wave, specifically a compression wave pushing through air, molecules being squeezed together and pulled apart in a ripple that your ear reads as noise. The pitch is the frequency, how many compressions hit your eardrum per second. The volume is the amplitude, how extreme each compression is. Sound needs a medium to travel through, which is why space is completely silent regardless of what every science fiction film has insisted for 50 years. Now add heat. Thermodynamics is the physics of energy transfer, and its laws are essentially a list of things the universe will not let you get away with. The first law, conservation of energy again. Total energy is constant. You can convert it, but you cannot create or destroy it. There is no free energy. Anyone selling you a free energy machine is selling you nothing. The second law is where it gets interesting. Entropy, the measure of disorder in a system, always increases over time in a closed system. Things naturally drift from ordered to disordered, never the other way around on their own. Ice melts, rooms get messy, stars burn out. You can put energy in to reverse local entropy temporarily. You can tidy your room, but doing so increases entropy somewhere else in the process. The universe as a whole is getting more disordered, always, forever. This is called the arrow of time, and it is the physical reason the past is different from the future. Drop a glass and it shatters. You will never watch a shattered glass spontaneously reassemble on your kitchen floor. Entropy is why. The third law. As temperature approaches absolute zero, the coldest possible temperature, entropy approaches a minimum. You can get very close to absolute zero. You cannot reach it. Nature has a floor, but no ceiling on disorder. Now let's change the subject completely. In the 1800s, a Scottish physicist named James Clerk Maxwell looked at electricity and magnetism, which everyone treated as separate phenomena, and showed they were two faces of a single force, electromagnetism. Charged particles produce electric fields, invisible regions of influence that push or pull other charged particles. Moving charged particles create magnetic fields. Here's the part that melted everyone's brain. A changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. Each one generates the other, leapfrogging through space as they travel. Maxwell ran the numbers and found this self-generating wave would travel at a specific speed. That speed matched the measured speed of light exactly. Light is an electromagnetic wave. It had always been an electromagnetic wave. Nobody had known until Maxwell noticed the numbers matched. This also predicted that other electromagnetic waves should exist at different frequencies. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, they are all the same thing at different frequencies. The visible light your eye detects is an extremely thin slice of an enormous spectrum. The universe is constantly broadcasting in every frequency simultaneously. You are only picking up one narrow band. Everything so far is classical physics. It works brilliantly. It also falls apart at very high speeds and very small scales. At very high speeds, you need Einstein. In 1905, Albert Einstein published Special Relativity, which starts with two premises that sound reasonable and produces consequences that sound completely insane. Premise 1. The laws of physics are identical for everyone, regardless of how fast they're moving relative to each other. Premise 2. The speed of light is the same for every observer, regardless of how fast the source or the observer is moving. No exceptions. From just those two ideas, Einstein derived the following. Time passes more slowly for objects moving at high speeds relative to a stationary observer. This is time dilation, and it is real, measurable, and has been verified thousands of times. The GPS satellites in orbit experience time very slightly differently from clocks on the ground due to their speed and altitude combined, and that difference has to be corrected in the software, or every GPS on Earth would drift by roughly 11 kilometers per day. Relativity is not philosophical speculation. It is running inside every navigation system on the planet right now. Also from special relativity, lengths contract in the direction of motion at high speeds, and mass and energy are the same thing at different scales, which is what Einstein's most famous equation actually says. A tiny amount of mass can release an enormous amount of energy. How enormous? Rearranging that relationship is what powers the sun, every nuclear reactor, and every nuclear weapon. The sun converts roughly 4 million tons of mass into energy every single second. It has been doing this for about 5 billion years. It has enough fuel for roughly another 5 billion. Special relativity handles flat space and constant motion. General relativity, published 10 years later, extends this to acceleration and gravity. And the core idea of general relativity is one of the most mind-altering things ever committed to paper. Gravity is not a force. Gravity is the curvature of space-time caused by mass. Massive objects warp the fabric of space and time around them, and other objects moving through that curved space-time follow curved paths. What looks like a gravitational pull is actually an object following the straightest possible path through curved space. Earth does not pull the moon. Earth warps the space-time around it, and the moon follows the curve. General relativity predicted that light bends around massive objects, that time passes more slowly near massive objects, and that accelerating massive objects would send ripples through spacetime itself. Those ripples are gravitational waves, and in 2015, 100 years after Einstein predicted them, two massive black holes merged over 1 billion light-years away, and the resulting ripple passed through Earth, compressing and stretching the detectors by less than 1,000th the diameter of a proton. Scientists detected it. The universe had been rippling since long before humans existed, and we are, extraordinarily, beginning to feel it. Now we go smaller, much smaller, because at the scale of atoms and below, neither Newton nor Einstein gives you the full picture. For that you need quantum mechanics, the most successful and most philosophically unsettling theory in the history of science. It starts with light again. Einstein, in the same year he published Special Relativity, showed that light behaves not just like a wave, but like a stream of discrete particles called photons, each carrying a specific packet of energy. This was the first crack in the wave-only model and the opening move in what became wave-particle duality, the discovery that things at the quantum scale behave like waves in some experiments and like particles in others, depending entirely on how you interact with them. Electrons, photons, atoms, all of them exhibit this dual nature, and it is not that they are secretly one or the other and we just cannot tell. They are genuinely both until measurement forces a choice. The universe at small scales does not commit. The double-slit experiment is where this gets genuinely strange. Fire electrons one at a time through two parallel slits at a screen behind them. Classically, you'd expect two lines where the electrons hit. What actually appears is an interference pattern, the striped pattern you get when two waves overlap. Each individual electron, fired alone, with no other electron to interfere with, still produces an interference pattern over time. It behaved like a wave, passing through both slits simultaneously, and interfered with itself. Now put a detector at the slits to find out which one the electron went through. The interference pattern disappears. Suddenly it behaves like a particle again, going through one slit or the other. The act of observing which path it took destroyed the wave behavior. The universe is apparently watching you watch it, and changing what it shows you depending on whether you're looking. Werner Heisenberg then made it worse with the uncertainty principle. There are pairs of physical properties, like position and momentum, that cannot both be precisely known at the same time. This is not a measurement problem or a limitation of our instruments. It is a fundamental feature of reality itself. The more precisely you pin down where a particle is, the less precisely you can know how fast it's moving, and vice versa. The universe has built-in fuzziness at small scales, and that fuzziness is not a flaw. It is load-bearing. Erwin Schrödinger formalized all of this into a wave function, a description of all the possible states a quantum system can be in along with the probability of finding it in each one. Before measurement, the particle is not in one state, and we just don't know which one. It is genuinely in a superposition of all possible states simultaneously. Schrödinger illustrated this absurdity with a thought experiment, a cat in a sealed box with a radioactive atom and a poison mechanism. Until you open the box, the atom has both decayed and not decayed, which technically means the cat is both alive and dead at the same time. He invented the example to show how ridiculous quantum mechanics sounded when scaled up. Physicists still argue over what superposition actually means at a philosophical level, which is a good sign something genuinely important is being pointed at. Then there is quantum entanglement. Two particles interact and become entangled, their quantum states linked regardless of the distance between them. Measure one particle and its entangled partner instantly reflects the corresponding state, no matter how far apart they are. Einstein called this spooky action at a distance and spent years insisting it must be wrong, that hidden variables must be doing the linking locally. Experiments in the 1980s and every decade since have definitively shown he was wrong about this one. Entanglement is real. This does not allow faster-than-light communication. The correlation is random until you compare results through a normal channel, but it remains the universe doing something that should be impossible by any classical account. The framework that unifies quantum mechanics with electromagnetism and the other particle-scale forces is the standard model of particle physics. It describes every known fundamental particle and 3 of the 4 known forces of nature. Matter is made of fermions, quarks, which combine to form protons and neutrons, and leptons, which include electrons and neutrinos. Forces are carried by bosons, Photons carry electromagnetism, gluons carry the strong nuclear force holding atomic nuclei together, and W and Z bosons carry the weak nuclear force responsible for radioactive decay. The Higgs boson, confirmed in 2012 after a 40-year search and the construction of the largest machine in human history, is the particle associated with the Higgs field, which gives other particles their mass. The Standard Model's predictions match experimental measurements to more decimal places than almost anything else in science. Worth pausing on those two nuclear forces for a second because they do things that don't get enough attention. The strong nuclear force is the most powerful force in nature, binding quarks together inside protons and neutrons so tightly that it takes an enormous amount of energy to pull them apart. Nuclear fission, splitting heavy atoms, releases the energy stored in that binding. Nuclear fusion, forcing light atoms together, releases even more. The sun fuses roughly 600 million tons of hydrogen into helium every single second. That is where sunlight comes from. The weak nuclear force, meanwhile, is responsible for radioactive decay and for changing one type of quark into another, which is how neutrons turn into protons inside unstable nuclei. It is also essential to the nuclear reactions that power stars and to the production of neutrinos, the ghostly particles that pass through ordinary matter almost completely without interacting. About 65 billion neutrinos from the sun pass through every square centimeter of your body every second. You cannot feel them. They do not care. It also has one glaring hole: gravity. Gravity is not in the Standard Model. General relativity and quantum mechanics are the two most successful physical theories humans have ever produced, and they are fundamentally incompatible with each other. Applying quantum methods to gravity produces infinities that cannot be cancelled out, and applying relativistic methods to quantum scales breaks the mathematics entirely. Reconciling them is the central unsolved problem in all of physics. String theory, loop quantum gravity, and several other frameworks have been proposed. None has been confirmed. The universe is apparently not done being strange. Now zoom all the way out. About 13.8 billion years ago, all the matter and energy and space in the observable universe existed compressed into an infinitesimally small, unimaginably hot state. Then the Big Bang happened. Space itself began expanding. As it expanded and cooled, the fundamental forces separated from an initial unified state. Quarks formed, then protons and neutrons, then the first hydrogen and helium nuclei, then the first atoms, then gravity clumped those atoms into clouds that collapsed under their own weight into the first stars. Inside those stars, nuclear fusion under crushing pressure and temperature forged every heavier element in existence. Carbon, oxygen, nitrogen, iron, all of it, through sequences of fusion reactions building heavier and heavier nuclei. Stars burned through their fuel and exploded in supernovae, scattering those elements across interstellar space. Later generations of stars formed, surrounded by disks of that scattered material, which clumped into planets, moons, and asteroids. On at least one of those planets, the chemistry got complicated enough to produce self-replicating molecules, and 4 billion years of evolution later, something made of that scattered stellar material is watching this video and mildly questioning its life choices. The carbon in your body was forged in the core of a star. The iron in your blood came from a star that exploded. You are, in the most literal physical sense, star material that assembled itself into something capable of being confused about quantum mechanics. The observable universe is about 93 billion light-years across. There are an estimated 2 trillion galaxies in it, each containing hundreds of billions of stars. The numbers are too large to meaningfully picture, which is probably why most people just shrug and order something from the internet instead. But here is the part that really puts things in perspective. The universe does not stop at the edge of what we can observe. Light from beyond a certain distance has not had enough time to reach us yet, because the universe has only existed for 13.8 billion years and light travels at a finite speed. There could be vastly more universe beyond what we can see, operating by the same rules, possibly forever. We have no way to know. The universe is still expanding. Not only that, the expansion is accelerating. Whatever is driving that acceleration, and we genuinely do not know what it is, physicists call dark energy, and it accounts for roughly 68% of the total energy content of the universe. Then there is dark matter, which does not emit or absorb light, but does exert gravitational effects. Galaxies spin in ways that only make sense if there is far more mass in them than we can see. That invisible mass is dark matter, making up roughly 27% of the universe. Add them together, and dark matter plus dark energy account for 95% of everything that exists. Every star, planet, atom, and particle described by the Standard Model, everything you have ever seen, touched, or studied, accounts for about 5% of the universe. The other 95% is made of things we cannot directly detect and do not yet understand. So that's physics. Classical mechanics explains how things move and why forces behave the way they do. Thermodynamics explains how energy flows and why the universe trends toward disorder over time, relentlessly without exception. Electromagnetism explains light, electricity, magnetism, and the entire spectrum of radiation the universe produces constantly in every direction. Special relativity explains time dilation, length contraction, and why mass and energy are interchangeable at a rate that powers stars. General relativity explains gravity as curved spacetime and predicted black holes and gravitational waves a century before we had instruments sensitive enough to detect them. Quantum mechanics explains the behavior of everything at the smallest scales and reveals a universe that is fundamentally probabilistic, fuzzy, and stranger than anything classical intuition can comfortably hold. The Standard Model catalogues the particles and forces that make up all visible matter, including the nuclear forces quietly holding every atom in your body together right now. Cosmology shows you a universe 13.8 billion years old, mostly made of invisible stuff we cannot explain, still expanding and accelerating, and built entirely from the scattered debris of ancient exploding stars. If your head hurts right now, that is the correct response. Physics is not counterintuitive because you're failing to understand it. It is counterintuitive because your brain evolved to track movement on a savanna and read faces in a crowd, not to picture the curvature of spacetime around a black hole or a particle with no definite position until you look at it. The mathematics handles all the parts that intuition cannot reach. And the mathematics works. Every phone, satellite, laser, MRI scanner, and nuclear reactor running right now is proof that humans figured out the rules of a universe that had absolutely no obligation to be comprehensible at all. That it is even partially is the most astonishing fact in science. The universe did not have to make sense. It does anyway, mostly. That is how the universe works. Explained fast. Zero equations. Mild to severe existential recalibration included at no extra charge. If you survived this one and want to actually pass your physics exam, save it, re-watch it, and hit like.